Okay, this is part 2 in our series on the hybrid rocket engine. In the first video, what I did is compared and contrasted solid rocket engines and liquid rocket engines with hybrid rocket engines. These essentially involve a liquid oxidizer that's pumped into a rocket tube that already contains a solid rocket fuel. And I made pretty strong arguments in favor of this design in terms of its simplicity, its safety, and its high performance. It's a particularly interesting design if you're a DIY project builder or you're an advanced amateur or even a university group. Now, I followed that part of the video with an explanation of how to deal with liquid nitrous oxide and how to get nitrous oxide to work with a rocket engine. Today, what we're going to do is I'm going to show you how to fabricate the fuel grains as well as how to design and fabricate the nozzles that work with a hybrid rocket engine. In the first video, I explained that anything that burns can be used inside of the rocket tube with a hybrid rocket. You can use rubber, plastic, you can cast it out of epoxy, you can even 3D print it. But the highest performance, greatest amount of thrust is going to be produced when you use paraffin, candle wax. And it's very inexpensive, it is non-toxic, it's widely available, it even smells pretty nice. There are some special considerations, though, in dealing with the wax, and I'm going to show you how to handle some of those problems in order to fabricate a very successful fuel grain. Now, in the simplest rocket engines, you simply take a tube, you pack it with the propellant or the fuel, and you put a nozzle on the end, and you've got a rocket engine. But as the rocket engines become larger and longer, it becomes impractical to pack it with all of the material reliably. And so typically what the rocket builder will do is they will fabricate what are called fuel grains. These are individual segments, small segments, that are designed to slip fit inside of the pressure tube. This is a lot easier to work with because of its small dimensions, and it's safer. Now, a rocket grain like this can be burned in either an end grained or a core, an end burn or a core burning design. In a very, very small rocket, you can pack the rocket with the propellant or the fuel grain and then ignite it from the nozzle end and allow it to burn toward the front bulkhead. The problem there, though, is as soon as the fuel or the propellant exposes the inner walls of the pressure chamber near the nozzle, that area is then exposed to the very high temperature gases for the full duration of the burn and can potentially pop through unless you're using a very, very temperature insensitive material like stainless steel. Much more commonly, you will build a fuel grain that has a central core burning design, where all of the combustion occurs on the inside of the fuel grain or the propellant grain and burns outward toward the outer wall. That means that the fuel or the propellant acts as an insulator to protect the wall from the high temperatures until the last couple of milliseconds of burn. Now, when you're fabricating a fuel grain like this, typically what you'll do is you'll take a paper, plastic, or phenolic liner like this that is designed to slip fit inside of the tube that you're going to eventually put it inside of. And then you will attach it to some sort of a surface and you will fill it with either a sugar propellant or a composite propellant. Now, if you're building an end grain design, you're done. But if you're going to build a core design, some people will actually insert a plug or a rod into the mold so that you will cast the final end product. I have found in these small scales, it's actually easier to fabricate a complete cylindrical grain and then post-casting, drill it out by using a small drill guide like this to guide a hand drill or a drill press and produce a final result. It works very well. However, when you are casting wax, you have a special problem, and that can be shown over here. You see this beaker This is containing warm, liquefied paraffin. If I take a piece of solid paraffin like this and drop it into the beaker, you'll see that it sinks right to the bottom. The reason that happens is because the solid paraffin is much denser than the liquid paraffin. You're never going to have a disaster of the Titanic on a wax ocean. The icebergs would sink to the bottom. The problem for us is because of that significant reduction in volume. If you were to pour that liquid paraffin into a mold like this, what would happen is it would shrink substantially and you'll end up with a much smaller volume than you started out with. Now you might think, well, wait a minute, if you know what the exact shrinkage level is, what you could do is cast a grain that's a little oversized and then it'll end up fitting inside your tube. That won't work. The problem being that when you fill up the grain or the tube with the liquid, it will cool on its outer surfaces first because that's where it's radiating heat into the environment. So the outer surfaces and the bottom will freeze into those final dimensions, which is kind of convenient because at least we have a tube we know will fit. But it also means that as it freezes or it solidifies, that void left behind, that volume deficit, then has to be made up by the liquid in the center of the grain as it flows into that missing volume. And you end up getting a huge divot at the top of your fuel grain. This isn't good because even though you're going to end up coring a lot of this out, you're still going to end up with convex mating or concave mating surfaces. This will produce a very strange internal volume during the burn and also exposes the walls very early on to the burn temperatures as the fuel or the propellant is consumed. What we want is a simple cylinder with plain surfaces that mate very well inside of the tube. Now, in order to do that, what you might think is, well, why don't you just make the tube extra long and then cut off that defective section at the end? And that is the answer. But it's a little tough to cut through both the cardboard or the plastic and the wax at the same time. So what you do is you artificially make the tube longer by wrapping a couple of layers of painter's tape around the tube, making it appear taller. Fill it all the way to the top, and then within a few seconds, you can peel the tape off and you end up with this exposed section that can just be cut off with a razor blade and then eventually drilled out. Now you might be thinking, that's a lot of waste. You're wasting all this wax, you're wasting the wax that you're drilling. You're not, because this is not a cured product, it's a melt. So whatever you remove from these grains, you can simply scoop it up, put it back in the pot, and reuse it. So not only is this wax extremely inexpensive, but you don't waste much either. Another thing that you may notice when you're looking at these grains is that these are black, and the wax over here is clear or at best white translucent. The reason that we need to do this is because inside of a rocket engine, the extremely hot exhaust produces a lot of radiant energy, both in the visible and the near IR. And that heat energy would transmit all the way through the grain and cause the grain to warm up. Within a few seconds, it's not going to melt the grain, but you actually want all that radiant energy to be absorbed within the first few microns of the surface, causing that layer to superheat, to melt, to vaporize, and to be able to blend with the nitrous oxide to produce the exhaust. What we do to achieve that is simply add carbon black. This is a nanoscale size particle of carbon. It's basically soot. And when mixed in with the wax at a 1% by weight ratio, you end up producing a very opaque, black, waxy candle. And this will absorb the light and also has a second advantage in that it toughens the wax grains. If you've ever taken a candle and you've snapped it, you notice that it not only cracks, but it often fragments into chunks. That's not good in a grain that could potentially be under the pressures and the vibrations inside of an engine. And so what happens by adding the carbon black is similar to what happens when you make advanced composites using nanoscale powders. You interrupt the fracture paths so that even though the wax grain can fracture, it doesn't create these catastrophic centimeter-long cracks. They're limited to, say, micron-long cracks. They'll still occur, but the wax grain will stay intact. So the carbon has the added benefit of making the wax grain tougher. And finally, it makes the grain a little bit more sinister, which is not necessarily a bad thing either. So let's go ahead and I'm going to show you how I actually cast these things, give you an idea of what little tricks you can use to make these things work well. Okay, so we've replaced the beaker with my dedicated wax melting pot. This is never going to be used again to bake beans. But what's nice about having a dedicated vessel for melting all the wax is that whenever I use up a quantity of wax and I want to replace it with either offcut from the trimming operation or additional wax, all I have to do is add a certain weight of wax, multiply that by 1% and add that much carbon black. So I've constantly got the same mixture in here. I'm always renewing it with the same percentages. And then when I'm done with the operation, I just let this cool and I can store this. And that saves a lot of materials and time because I'm not washing this out and cleaning it out. I can just keep reusing this over and over and over again. Now, if you look inside of here, you'll see that the carbon black has been placed in here. And when I place wax inside of here, this is 100 grams of wax, I will add 1 gram of the carbon black. You want to be pretty careful with this. I added this in here with a mask on, but in general, this is not good stuff to breathe. So if you're going to be doing a lot of moving around, you probably want to wear a mask. So I'm being a bad boy. But in any case, we're going to give this a couple of minutes to melt, and then I'm going to show you the properties of what kind of material, what kind of state you want this in order to be able to fill these up. All right, we've taken about 5 minutes here, and we have allowed that wax to melt. And if you look at the bottom, this is important. I don't know if you'll see in there, but the carbon does not dissolve in the wax. It's suspended. And over time, eventually, that carbon would settle down to the bottom of the pot. So whenever I'm adding this or using this to cast, I have to stir it first to make sure that the carbon is well suspended in the liquid paraffin. And that presents a little bit of a problem because if you look at the original fuel grain that I poured in one go, the top of this fuel grain is a lot lighter than these others. Because this took long enough for this to finally solidify, the carbon had a lot of time to settle down to the bottom of the container, which isn't that helpful. And so what you need to do is, rather than add this in one big go, what you do is you take a small spoon, plastic is fine because you can throw it out, give it a little bit of a stir, and then you're going to only want to add about 10 or 15% of the volume of the final grain to each one of the cylinders. Not very much. Try not to spill too much. And then what you're going to do is you're going to wait about 5 minutes. Okay, it's been 5 minutes. The reason you do that is because the small volume of wax will cool relatively quickly and doesn't give the carbon a lot of time to settle down to the bottom. In addition, what that does is it allows the wax to begin to solidify, begin to shrink, but still remains warm enough that after about 5 minutes or so, I can go ahead and add another little sample of the very hot liquid wax to the warm, softened, but still solidified wax, and they'll form a very good bond. You won't get any delamination. In addition, the wax that we're adding can fill the small crater that is beginning to form at the top of the thin surface. This has another benefit beside the settling of the carbon, and that is if you form a large wax grain in sort of one go like this, especially if they're even bigger than this, because the outer surfaces harden in their final dimensions. If the inside is still molten and liquid, what it will be doing is shrinking, but the outsides can't give. And so you'll create a lot of stresses in the wax grain that can cause it to fracture. By pouring this in small, thin little sections like this, even though you'll get the same total amount of contraction, the absolute amount of contraction in each layer is much less. And so the stresses that you create inside the fuel grain are a lot less. Now you might think, wait a minute, that's going to take forever. I'm adding like 15% of the volume of this wax each time I put a layer in here like this. And then I'm waiting 5 minutes between each one of these additions. It's going to take me an hour to pour one of these grains. And that's true, it will take you that long. But kind of like painting the Golden Gate Bridge, it'll take you an hour to do one of these, and it'll take you about an hour and 10 minutes to do 25 of them. Because if you line up a whole bunch of these and you start filling them, by the time you get to the last one, you basically can start again with the next layer. So the way to do this is to set up a whole bunch of these tubes, everything's taped up, fill them in one go in an afternoon. Then when you're done and everything is cured and you take off the tape and you slice it and you drill it and you pop them off, you have a whole bunch of fuel grains. That's what I did. I took a whole bunch of them and I put them in a box like this, and because they're wax, they're basically candles. They're barely flammable. They don't absorb moisture. They'll be good for a century. So you can make up a whole bunch of these fuel grains and then build up motors whenever you care to. It's a really nice technique and saves a lot of time and effort. So basically, I've showed you how to produce one of these fuel grains, and as we will demonstrate, they really do work. But now what I want to do is shift gears a little bit, and I want to go over and explain to you sort of how a rocket nozzle works, how you design the parameters of a rocket nozzle. Now, in a simple sense, if you simply took some composite fuel and you threw it into a campfire, you'd get a spectacular ball of flame, but you're not going to get any thrust. If you take that same composite and you put it inside of a tube like this and ignite it, like we did in our videos on the ignition systems, just an open tube, you'll get a big fountain of flame coming out of one end and a very tiny amount of thrust in the opposite direction, simply because we have directed the kinetic energy, the momentum of that gas in one axis. But we get almost no thrust because we're building up almost no pressure in here, and so the velocity of the gas coming out is very, very slow. The simplest thing that a nozzle does is it acts as a restrictor plate. It effectively increases the pressure inside the combustion chamber, and that drives the gas to higher velocities. Same principle, putting your thumb over the end of a hose. You increase the pressure in the hose, and that drives the water to a higher velocity and gives you more reactive thrust. This restriction plate, by increasing the pressure inside of the engine, you also create a more efficient conversion of the chemical or thermal energy generated by the burn into work, into, in this case, kinetic velocity of the particles. It is the same reason why a diesel engine is more efficient than a gasoline engine. The higher the pressure you can achieve inside of your combustion chamber, short of blowing up the motor, the more efficiently you can convert that into useful work. You can never convert all of it, but you'll convert a larger fraction of it if you run at very high combustion chamber pressures. So that's the major thing that the throat or the restrictive orifice does in a nozzle. There's a problem, though, with this simple design, because what happens is the gas inside is at a very high pressure, but it's not really moving. And right at the entrance to the orifice, all of a sudden the gas has to accelerate to its final velocity almost instantaneously. There are a lot of turbulent eddies that are created at that instant transition zone, and that creates an inefficiency in that transfer of energy from one form to another. So a solution to that problem is to create the convergent section of the nozzle. This is inside of the tube, and effectively what it does is it gives more time for the gas molecules to accelerate to the final same throat diameter or restrictive throat or orifice in the nozzle's narrowest part. By being gradual like this, it's a more efficient way to convert that energy. Now, that convergent section there can be very, very narrow. It can be very, very gradual. You could have a very gradual taper. It's generally not a good idea because in order to do that, you'd have to make the nozzle much longer, make the rocket much longer without adding any propellant, so that decreases its efficiency. It also increases the surface area and more drag. At the same time, if you make this opening very, very broad, you end up approaching the inefficiency of an orifice. A general rule of thumb is 90 degrees. You want the angle of your convergent section to be 45 and 45 or an included 90-degree angle. Now, what happens inside of the convergence section is kind of interesting. The pressure actually drops inside the combustion chamber in this tapered zone. Now, you can imagine why that has to happen, because if the gas is moving from the combustion chamber out, the only way the gas is going to flow in one direction is if it's flowing from a higher to a lower pressure. It's just a fact. There's no other way to get the gas to move in that direction. The principle behind what's happening, though, involves Bernoulli's principle. If you look at a room like this with 6 sides to it and a stagnant mass of air, what creates the pressure against all of the walls is the sum total of the trillions upon trillions of gas molecules that are rebounding from the surface of the walls. That momentum transfer is pressure. The mass of the particles times the mean velocity that they're bouncing off the walls at. And that velocity at sea level and at room temperature is approximately 330 meters per second, or 1,100 feet per second, or the speed of sound. What happens inside of a room like this when you open up 2 of the walls and you allow the gas to begin moving through the room in one direction, because of the conservation of energy, as long as you don't add heat to increase that kinetic energy or that velocity, a larger component of that velocity is along the axis of motion. So to reach the same net total, the velocity lateral to that axis of motion has to decrease. The average has to decrease. And that's why the pressure goes down in a gas moving through a tube as opposed to the gas stagnant in the tube. As the gas is accelerating in the convergence section of the nozzle, the pressure is dropping. Now, what accelerates the gas inside of that convergence zone is the rebounding off of its brothers in the train, in the cars behind it. They're transferring some of their kinetic energy to the particles in front, causing them to move faster. As the gas continues to accelerate and move closer and closer to the speed of sound, it gets harder and harder for those particles behind to overtake and transfer any kinetic energy. Eventually, when those gas molecules reach the speed of sound, they can't go any faster, because if they were to do so, they would have to get an impact from particles that can't catch them anymore. They can't overtake them. So the speed limit on the convergence zone is always at Mach 1. It can't go any faster. So if you continue to produce more gas behind there, the only thing that can happen is the pressure has to increase throughout the entire chamber, including the convergence section. What happens on the output side of the nozzle is that that gas that's now moving at Mach 1 under pressure enters an environment at a lower pressure. But there's potential energy in that pressurized gas, and that potential energy is converted into additional velocity. They will recoil away from each other and accelerate beyond their starting speed of Mach 1 and become supersonic. And that's good. We want high velocities. The problem with that, though, is, like I said with the convergence section, this is a rather inefficient way to do this sudden expansion. In addition, the gas is going to be expanding in a hemispherical zone all the way around the nozzle, not only going in the direction you want the rocket not to go in, but also laterally. And this is useless. It's wasted kinetic energy. So the final third part of the engine is what's called the divergence section. This gradually expanding cone behind the throat, or the orifice, the restrictive throat of the engine, gives a gradual decrease in pressure and increase in velocity, and that's more efficient. It also tends to redirect the lateral particles in the axis of the motion of the engine, giving you the thrust that you want. And this expansion, the amount of expansion, depends on the difference between the pressure in the combustion chamber, which you want as high as you can get, and the pressure outside. If you're in space, you're in orbit, because there is no pressure outside the engine, basically these particles will continue to expand forever. And so by making this nozzle very, very big, you can tweak out ever smaller amounts of additional efficiency or thrust, basically forever. And the only real limitation is just the bulk of the nozzle as it becomes bigger and bigger to try to get that last little bit of efficiency. If you look at the Raptor engines, for example, the sea-level Raptors have a much smaller nozzle than the vacuum operation Raptors because they can extract a little bit more power by taking advantage of the fact that they're flying in a vacuum. Now, the amount of expansion, when should you stop, at sea level, is then therefore the ratio between the inside pressures and 1 atmosphere. And as a good rule of thumb, what you can assume is that for every 12 atmospheres of pressure in your combustion chamber, you want to add again the area of the throat of your nozzle. So for example, if you're running 12 atmospheres inside of the engine, you want the exit or exhaust from your divergent section to have twice the area of the throat of your nozzle, or the square root of 2, or 1.4 times the diameter. If you're running 60 atmospheres in the combustion chamber, which is typical of most of these rocket engines, you want an increase of area here of about 5 to 6 times the area of the throat. So about 2.2 to 2.4 times the diameter. And finally, the angle. The expanding angle needs to be a little bit more gentle than the convergent angle. And so effectively, what's been found to be pretty close to optimum is a total of 30 degrees. So 15 degrees and 15 degrees in the divergent section of your nozzle, and you're pretty much set. So the nozzle consists of 3 parts: a convergent section at 90 degrees, a throat that's minimal diameter to get the highest pressures possible, and a divergent section that has 30 degrees of angle, and the ratio here depends on what pressures you have here and the atmosphere. That's pretty much it. That's the design. Now, the materials that you use to fabricate the nozzle depend on how sophisticated the rocket is. In the simplest rocket engines, you can use bentonite clay, basically kitty litter, and force it into the shape of a divergent convergent nozzle. You can also cast it from concrete. However, those things tend to be relatively fragile and, in general, not as light as simply getting a plastic commercial nozzle. This plastic material, you can get small nozzles for a couple of bucks, so they're pretty inexpensive. They're lightweight and they're made out of a formaldehyde or urea formaldehyde resin that doesn't melt. It chars or it ablates. And so when reinforced with glass particles, is very tough and will hold up to at least one firing of a typical composite or sugar rocket. The problem is with a hybrid rocket engine. Not only is the temperature in that engine extremely high, but the highest efficiencies are gained when you're no longer running a fuel-rich or at least a neutral environment like a composite or a sugar rocket. You're running an oxidizing environment. So it's oxygen-rich and thousands of degrees and will burn through one of these phenolic nozzles in about 1 second. So ultimately, you'd have to use either a very high temperature metal like Iconal or even tungsten, or better yet, use something like graphite. This is isostatically molded microfine particle graphite. It's supplied in rods. You can get this in 1 meter long rods, and it's not that expensive. This rod here was about 70 bucks. This was about $105 for a 1 meter length, and you could make about 20 nozzles out of one of these. The melting point of graphite at 100 atmospheres is about 4,300 degrees centigrade, way beyond the melting point of even tungsten. And even at just 1 atmosphere, the sublimation rate or the ablation temperature for graphite is about 3,600 degrees centigrade. So these things are remarkably tolerant to temperature and even somewhat tolerant to the oxidizing environment in a hybrid engine. For example, this particular nozzle that I made has been through 4 firings, and the throat on this nozzle has only increased in diameter by a few microns. So it's a very robust material. It's not very heavy. It's relatively easy to machine. It stains the heck out of your hands, and there are some special tricks to working with it, and I'm going to show you how to build one of these nozzles over here. So let's take a look. All right, so we're going to be fabricating some of the smaller nozzles for one of the engines. And I've cut off a segment of the graphite. This slices very easily with a hacksaw or a cutoff saw. And one of the things to be aware of when you're dealing with graphite is it tends to be abrasive, so you want to use very hard tooling. Carbide is great if you've got carbide inserts, because I haven't found any of them to wear out after about 10 nozzles. Regular tool steel doesn't last that long, so if you can use carbide nozzles, you're in a better state. The second thing is you want to cut at very low velocities, not because this overheats or there's any sort of a tooling reason, simply because you generate less kinetic energy in the particles and you don't drive the dust that's created when you machine the graphite broadly into the atmosphere. And finally, one of the things that I set up here is I took our shop vac, mounted it on a little support here behind the lathe to pull out some of the finest dust. That's probably the biggest safety reason, or safety method of dealing with graphite, is to get rid of the finest particles. The larger chunks will just fall to the ground and you can sweep them up, so it's not a big deal. So I'm going to get started, and it's going to get pretty loud in here, so we're going to be depending either on written inserts, or we're going to have to do this as a post-production overlay in terms of audio, because it's going to get kind of loud. All right, so I'm finished with a nozzle. It's nice that you can reuse them, and certainly if you had a CNC mill, you could pop these things out in a couple of minutes, but it's fun to experiment with a manual mill if you're going to be doing little adjustments and trying to figure out better techniques. A little trick that I found is that final finishing with a Scotch-Brite pad, the maroon pads, produces a very smooth surface, and you can see that this is almost flawless and is typical of the other nozzles that I made for the smaller engines. In addition, one of the things I did is you can see that I wore my Tech Ingredients t-shirt. That's not just to show off the logo, it's also to show the fact that despite the gloves and despite a little bit of powder on the floor, you can see that I'm clean. The vacuum works very well in picking up any of the very fine dust, and the stuff down there is easy to sweep up. So it's a little bit messy, but it's not horrible. Wearing a pair of gloves is also not a bad idea. The stuff gets in your nails and it's there for a week. In any case, now that we know how to make the nozzles and the fuel grains, we know how to deal with the nitrous oxide. What we're going to do in the next video is I'm going to get into the oxygen augmented starting system. Hybrid engines need a different way to start than a typical composite or sugar rocket engine. It's kind of interesting the way that we did that. In addition, we're going to review and go through the systems that we use to test this. Not only the safety systems and the backup systems, but also the computerized data logging system to give you an idea of how this test is going to be performed, you get an idea of some of the data that we can acquire. So I want to thank you very much for watching, and I want to advise you to stay safe, but this is one of the safest rocket engines I think you can work with. In addition, if you have any questions, please put them in the comments below because I read them all, and if you have questions that I can answer, I try to answer as many as possible. And if you like what we're doing here, please let people know. The bigger we get, the more we can afford to do, and the more reward we get for the kind of effort that we put into these videos. So you have a great evening, stay safe, have fun, and we'll see you soon. Good night. What you should do is put all this black around my nose, like you don't use the mask, and you clearly have like all this carbon black right around your mouth. Like not only did you not use the mask, but somehow your face is just completely covered like you're a coal miner. It's like much worse. Sure.